So we're starting with this molecule called trans-anethol. You can visually count. It's got a benzene ring, that's 4 degrees of unsaturation, and has an alkene, that's another 1, so it's 5 total. We have proton NMR, we have the expansion. I don't recall in the exam if the spectra you're going to look at have expansions or not. But normally they tell you what the chemical shifts are, so pay attention to those things when you're counting. So there's proton, there's expansions. So I'm going to use the numbers they have here. So 1 here, 2, 3, down the chain there. Notice that I did not put in any numbers in terms of millimeter heights of these integral peaks. So this line that's called the integral, that S thing. And again, the software integrates the area under that curve. That's pretty much any modern analytical instrumentation does AUC, which is area under curve. It just math, it figures it out. Spits out a number. And so again, you want to be flexible in how you think. We've done a lot of this problem solving from the point of view where this is unknown. And so we have to figure things out. Is it CH, CH2, CH3? There, it's given to you. So I'm going to ask you some questions. Maybe what I can do, I don't want to do that. I'll do this. So I guess, yeah, all the expansions are listed down here. So I'm going to read off this number. So the peak at 1.8. Looking at the relative height of the integral, tell me a number, one of these numbers of that assignment. Which hydrogens does the peak at 1.8 belong to? This should be like an empty netter in hockey. I mean, this should be pretty easy. Is it?
Yeah. I said that so easy.
I don't want to zoom in because then it gets weird. I'll draw it on the board, and I'll draw the structure on the board. And again, do not self-defeat. Whatever impression you have coming into organic chemistry, whatever it is now, don't make the question harder than you might think it is. Let me ask the question another way. I'll write it on here. So, looking at this molecule, how many sp3 hybridized carbons do you see? And they are what numbers? So notice, I'm going to call this region between 4 and say 6 no man's land. You see nothing in there, right? How many peaks do you see that are less than 4? 4 ppm. I'm not asking about the multiplicity, just like the unique number of peaks. It's just 2. Again, do not overthink this. There's 2, right? Those 2 correspond to the sp3 hybridized carbons bearing hydrogens. Now, of those 2, we want to make the assignments. Which one belongs to the peak at 1.8, and which one belongs to the peak at 3.7? So 1.8 should be what? What? I'm not hearing like a unanimous like.
We're wondering like how and why.
At this point, this should be very obvious to you. You have 1 and 2, right? So those are both sp3. If you count the unique number of peaks, you have 1, 2, 3, 4, 5, 6 unique sets of H, right? So we're clear on that. Now, if you look at this region, there's 2, this region, there's 4. So if you count 1, 2, 3, 4, that's the other 4. Those belong to sp2 hybridized carbon. The difference between that and that, see how that's bonded to a heteroatom? And so when you're looking at where these peaks occur between 0 and 10, the location is indicative of the function group. This thing at 1 is that one right there. That most resembles, and whether you believe this or not, or it's not evident, maybe by the end of the semester it will be, or at some point a light will turn on. If I write this, so this is methane, CH4. If I take this H and I substitute this whole thing in there, methane CH4s, the H's in methane, let's say they occur around 0.5 ppm. That's the simplest hydrocarbon. So anytime you substitute, it moves it away from 0. So peaks normally occur like this sort of methane CH peak will be around 0. You've taken one of these H's off and you've put all this other crap on there. So it's moving it, it's shifting it. You've done the same thing here. Instead of CH4, you have CH3, then all of this, and that heteroatom really shifts it away from 0. So instead of 0, it's moved quite a bit more. The other telltale sign is the number of neighbors here. This has how many neighbors? That has no neighbors. So that is a singlet. So that's another way to tell what's what. So this peak at 3.7 is 8. At 1.8 is 1. So that's a doublet, right? For the most part. So why is that a doublet? So I'm going to say this is 8, this is 1, that's a singlet. So that looks sort of like a doublet, right? I don't know if you can see it or not, but each of those peaks of the doublet has another splitting. So that peak is that. There's your one neighbor, so that's why it's a doublet. That other little splitting comes from this proton here, because it's extended through that pi system.
Could you redefine
So let me draw it. I haven't, I guess, formally used this nomenclature in class, but I'll tell you now, we're gonna start using it. So look at carbon, carbon labeled 1, and I'm gonna call that the alpha carbon. That is the carbon of interest we are trying to assign. It has 3 hydrogens. So a neighbor is right next door. It only has 1 neighboring carbon, correct? So I'm gonna call that the beta carbon. You have to look at all the beta carbons and count all those hydrogens. Since there's only 1 beta carbon, it only has 1 hydrogen. The n plus 1 is 1 plus 1 is 2, that's the doublet. This finer little splitting that you see is sort of beyond what we're learning, so it's not important. So when I say if this is the alpha carbon, there's this beta oxygen that has no hydrogens, so that's a singlet. So we've made 2 of the assignments so far. How many sp2 hybridized carbons do you see total? We have 7 versus 8. It's an epic battle. So I would say 8. So of those 8, and you can just read the numbers, which ones are bearing hydrogens? So 2, 3, 5, 5 prime, 6, 6 prime. So you've differentiated of those 8, 6 have hydrogen, 2 do not. And again, this is the logic you want to use to solve these problems in sort of an efficient manner. So try not to get bogged down on any one question. So now what we want to do is look at making the assignments in the, for lack of a better way of putting this, the sp2 region. And what I mean by that is those are hydrogens bonded to sp2 hybridized carbon. If you look at these ratios, you can see, just eyeballing, that is 2 times that, and these are 3 times that. So that's 1, 1, 2, 2, 3, and 3. So we don't really need a ruler, just trust your instinct. If these are both 1 and 1, from what a rough estimation, what assignments would you make to them? What numbers? So 2 and 3, right? That's just purely the integration. So we're going to say to this side we have 2 and 3, and this side we have the 5 and 6.
And that's the integration, which is how many hydrogens you need?
No, it's these numbers here. We're just trying to make the actual assignments at this point.
What's the 5 prime, 6 prime?
That would be just the other side here. Just call it 5 and 5 prime, 6 and 6 prime. So I want to point out something mildly interesting, maybe. So let's look at the one between 6 and 6.1. We already said that the peaks to the right of 6.5 were either 2 or 3. What do you think the peak at, say, between 6 and 6.1 belongs to? So 2. Can you explain why?
Because it has 4 neighbors, so it's gonna be like 4 plus 1, 5, so it's gonna be like a multiple.
Right. And so look at the one between 6.2 and 6.4. What does that most resemble? What peak shape? A doublet, which means it has one neighbor. So do not let your sort of maybe lack of theoretical understanding cloud your better judgment. That looks really complicated, right? So why does it look like that? What this is, it's a doublet, so that gives you a doublet. We're looking at this peak. It has that one neighbor, that's a doublet. That doublet is split by these 3 into a quartet. So this is called a doublet of quartets. Can you see those peak shapes in there? I'm doing a really bad job of selling this. Maybe take your eyeball and sort of like read this way. So see sort of that. The other line of that quartet is buried in there. So there's one quartet, there's the other. So in general, yes, we would call that a multiplet. Yes.
Can't you also throw that the second carbon is the one at 6.1 because it's further away from the benzene ring, so it would be more upfield than the other one? Just the multiplicity gives it away, but wouldn't it also be closer upfield because of what it's bonding to?
Yeah, that's another way you could describe that. It's distance away from the benzene ring. So this is 2, that's 3. Then these last 2, this is a classic 1,4 substitution pattern. Again, you have 3 possibilities when it's di-substituted benzene, 1,2, 1,3, and 1,4. You're looking for like the different peak shapes. So this is the 1,4. Any questions on that? Clear as mud. What? So I would say that towards 0 is shielding. So again, this is sort of beyond what we talked about in class at this point. So don't freak out and pretend you have to know this for the exam. This oxygen through resonance will push electron density onto 6. So between the 2, I would say this is 6. And that's 5. So the protons at 6 are shielded. The ones at 5 are de-shielded because this, in a different resonance form, this pi bond will withdraw electron density, and so you would end up with a plus charge there. Yep.
Would you be asking any like shielded questions on the test?
Not really. I don't really dig the nomenclature of shielding or de-shielding, so it's really better to just refer to the ppm shift. So let me take a peek at this. And then here's that cozy, and then I guess we're not gonna do this one because that's a different type of one, but we'll do the cozy one. The cozy is simply, what we're gonna do on there is just fill in the dots where the coupling should be. Normally, the spectra you would be given have the dots, then you find the correlations. This cozy here. I won't belabor the point. We said this was 1. That's 8. We said, I apologize for how tiny these peaks are. So that's 2, that's 3. What this, the cozy does not have any peaks drawn in, and we'll just briefly look at what you would do with this exercise. So I'm going to draw that diagonal in. So the peaks that occur on the diagonal are the identity, which means it's basically just looking at the spectrum itself. We saw from the prior thing, we said the protons of 1 were coupled to 2. So if you were to put in a peak here, if we start at, we're reading 1 and we're going to go down, we would have to go down until we hit 2. We would see a cross peak there. Alternatively, if you go down from 2 to 1, you would see a cross peak there. So the line is sort of pre-drawn in there. And again, I'm not going to like kill you on this, but that's sort of how you analyze these things. It's almost like if you take an axis and rotate it, the peaks mirror each other. Don't get a brain hemorrhage. This isn't going to be on the exam. No.
Okay, so I just want to make sure that I'm kind of understanding what's going on here. The cozy just shows which protons are like next to each other, I guess. Like.
Yeah. So let me draw this up here. If I put in H, we already saw that 1 and 2 were coupled. So what this is showing you is this. It's mapping out that relationship, and that's what you're seeing in this cross peak.
So it kind of shows which of the peaks are like on next to each other. So like
Yeah.
1 is next to 2.
Right.
Okay.
And if you've, like, what math class has like graph theory, but like, you look at, I don't know if you remember, I can't remember that movie with Matt Damon at Harvard. I'm really bad with like remembering things. So he's up at the board drawing this as like the janitor or whatever. No. Good Will Hunting. So like this thing I just drew up there, you get these like 2 position coordinates and you see they start overlapping, and that will eventually look like a chemical structure, is what you're doing here basically. The nosy we are definitely not going to talk about. Nosy basically means nuclear Overhauser effect spectroscopy, and that's so.